Okay, yeah, so I think just for the hell of it, I'll share my screen and share these slides that I've been making. So I'll try to give this, I will try to not give this as a talk in the way that I would do to my intended audience. But
how long is the talk?
As a talk, I'm supposed to. Oh no. Okay, I guess it's okay. As a talk, this is supposed to be. It's supposed to be an hour-long talk, I think.
Hour long.
Yeah. So as you know, I'm not going to give it in the same way, but so as you know, people like to talk about how mysterious and amazing and hard to understand motives are. And they start with this quote by Grothendieck, which sort of is part of the mystification
Sure.
of motives here. And so I'm trying to.
It does at least. I mean, that presumably that's a big hint there. It says geometry and arithmetic.
Yeah. So that's definitely a hint. Yeah. He wasn't trying to explain it here. This is from his list of his top 10 discoveries or something like that. Okay. But this is like my way of trying to get people to understand motives. So go back to the Riemann's work. So Riemann was trying to come up with I don't know if he was trying to, but he came up with a formula for the number of primes less than n. And it's this nice, interesting function here. And so his big discovery.
Well, but did you? Okay. Oh, sorry. Okay, I should be quiet now. Is that right? Until later. Okay. Okay.
Maybe.
We'll use that approach. Go ahead.
Okay. Yeah. So his big discovery was that you could write the prime counting function as a nice smooth function. It's like the integral of 1 over log x plus a bunch of wave-like functions, which you can think of as like corrections to that main thing, which is where there's one of them for each non-trivial 0 of the Riemann zeta function. And so here this k equals 398 shows that like you're adding the first 398 terms. And you can see it gets better and better. If you look really carefully, you see these little glitchy things, which are at prime powers. And that's actually because what he really first came up with is a formula for some other function that sort of cares about not just primes, but prime powers, which is probably like a hint of a million things, right? But like here, you can see this little glitch here at 9, and this little glitch here at 8, and this glitch here at 4, and so on. So that's really cool. But anyway, so there are these waves for each 0 of the Riemann zeta function. And so one way to think about it is just like a really vague way, maybe, is to think of primes as like particles, and zeros of the Riemann zeta function is labeling frequencies of waves. There's some kind of Fourier analysis stuff here, although it has to do, I guess, with a multiplicative group. So these waves aren't like sine waves. They're like, they wiggle slower when you go further out. So that's why the zeros of the Riemann zeta function are interesting from one point of view. And so the prime counting function is this main term, which is this integral of 1 over the logarithm function, plus these waves. And so if you knew exactly where these non-trivial Riemann zeta zeros were, then you'd know more stuff about the prime counting function. So that would be nice. And in fact, there's this nice restatement of the Riemann hypothesis in terms of the prime counting function. So the usual statement of the Riemann hypothesis, as you know, is that the non-trivial Riemann zeta zeros lie on the line real of z equals 1/2. But like another way to say it, which in some ways makes it more obvious one reason why you might care, is that it's equivalent to saying that the difference between the prime counting function and this main term, this integral of 1 over log x, is bounded. It's bounded by some number times the square root of n log n. So, and it's a square root of n because of this real of z being 1/2 actually. So to get interested in the Riemann zeta zeros, it's enough to be interested in prime numbers and how many there are in a less than n. So to get anywhere with the Riemann hypothesis, obviously it might be helpful to know what these Riemann zeta zeros actually are as kind of objects or things, instead of just providing these waves. Maybe they actually have some significance. And so that I think of as like one way that you could get interested in the Weil conjectures, which are because it's an easier context to ask that kind of question of what zeros of zeta functions are. And so in this in this Weil conjecture thing, you're trying to count the number of points on an algebraic variety over a finite field, like a field with p to the n elements as n increases. And the number of points has a main term plus some correction terms. And those correction terms are related to zeros and actually also poles of some kind of zeta function that you can attach to the finite field. But I'm not really talking about the Riemann hypothesis here, actually. What I really am talking about is motives. And so the cool part is that each of those correction terms is connected to a motive, which is an actual object of some sort. It's a thing. So that's what I'm going to try to say a little bit about, try to figure out what these motives are. Nobody really knows. So people have figured this out pretty well for these Weil conjectures, although there's various things about motives. But I should just admit right away that no one has like carried on and completely figured out how it's all supposed to work for the Riemann hypothesis. There's some nice work on that, like Yuri Monin has this nice paper on the zeta function and motives, where he tries to sketch out how you could try to prove the Riemann hypothesis using the same idea, but you would be using some different version of motives, and nobody has really gotten that to work. But oh well. So let's see. Sorry, but how did they get? Oh well. So here's an example. So suppose we're trying to count the number of solutions of some equation. So here's an easy one. Well, it's easy in a certain sense. Sorry. It's y squared plus y equals x cubed plus x. And we're looking at it over the finite field with 2 to the n elements. So I'm going to take my prime to be 2. And so we look at different powers of that prime. So obviously 2, 4, 8, 16, blah, 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 blah. And then so that's the number of elements in our field. And then here's the number of solutions of this equation. And if you look at it, you see all sorts of fun things. It would actually be really fun to teach a class sometime where you like teach people this stuff by just starting out, getting them to write computer programs or something to count these things, and like doing tons of examples and getting them to figure out the patterns.
Yes.
I'm not so good at doing that myself. But anyway, if you look at this thing, I mean, like one super obvious thing is that like when you get to 10, you get 1,024 elements in your field, and that's exactly the same number as elements in your in this curve here, in this. And you see, if you look backwards, you see, hey, that's also true here for 6. It's also true here for 2. And then even when it's wrong, it's not too far wrong.
Right.
So that makes you want to like subtract off the sort of basic guess that it just is p to the n from the. So that p to the n is going to be like this main term in this case. And then we subtract that off, and then we can start thinking about the more interesting, subtle stuff, which are these correction terms. So here I subtracted that off. And so here's like the number of solutions minus 2 to the n. And then now, wow, it looks really great, right? Because they're like all powers of 2. And but they're sort of funny. 2, 0, -4, 8, -8, 0, 16, -32, 32, 0. So if you stare at it, you see all sorts of stuff.
Yeah, it's very suggestive. Go ahead.
Yeah. So there's a kind of period 4 thing going on, like as 0 comes in.
Yeah.
If you look, it's sort of more like a period 8 thing, like positive, 0, negative, positive, negative, 0, positive, negative, and positive, 0, negative, positive. So like the sine pattern has period 8. So like you should expect, and it's growing sort of exponentially. So you expect that this should involve something connected to like an 8th root of unity times some number that's bigger than 1. And you're like raising it to bigger and bigger powers. But that would give you imaginary numbers. So you should be doing like that, but then like adding it to its complex conjugate so that you get something that's always real. So it's, in other words, some number to the n plus its complex conjugate to the n, where both those numbers are like some number times an 8th root of unity. So anyway, we're getting these oscillatory, so you could figure it all out just by staring at this for long enough. Yeah, you get these oscillatory correction terms, which are reminiscent in some sense to the Riemann hypothesis. So you could like work out what it actually is. And it turns out the number of solutions is 2 to the n, that's the main thing, minus 2 correction terms, which are powers of some number and its complex conjugate. This number here, -1 plus I, it has absolute value square root of 2. So it's like square root of 2 times an 8th root of unity, and the 2 conjugate ones. So that fits what we were seeing. You might not have noticed the minus sign just from until you like started calculating. The minus sign is incredibly interesting and important because it's not just a sum of powers of numbers. It's like got some powers of numbers and minus some other powers of numbers. So Hasse in 1933 figured out this stuff, proved this theorem for a number of points in an elliptic curve. And well, here I'm just talking about the solutions of a cubic equation that gives you an elliptic curve. So here I'm not putting in the pointed infinity that an elliptic curve needs to have to actually look like a torus yet. So the number, so it works just like we saw. It's like p to the n minus some number to the n minus its conjugate to the n, where those two numbers have the absolute value being the square root of p. So those two terms, these are the oscillating correction terms that grow slower than the main term. So of course, an elliptic curve, the projective variety, so it has a bit more to it than what I said. So just a point at infinity. So you really need one extra point if you're counting the points in the elliptic curve. So then we get like p to the n minus these numbers that have absolute value, the square root of p to the n plus this thing, which is, you can think of as like p to the 0, 1 to the n. So these 4 terms correspond in some cool way, which is sort of part of what Grothendieck was trying to understand in his work on the Weil conjectures, to the 4 parts of an elliptic curve over the complex numbers, which you can think of as having like a 0-dimensional homology bit, and then 2 1-dimensional homology pieces, and then a 2-dimensional homology piece. So those correspond to these 4 terms. And so the pieces of dimension k give the terms that grow like p to the k over 2 times n. That's where the square rooty stuff is coming in. So they generalized Hasse's work to curves of any old genus, and it works just if you just like had to guess how you would generalize it to higher genus, this is just what you'd guess, at least given the way I'm describing it. So if you have a curve of genus G, defined over the field with P elements, then the number of points over the field with P to the N elements will be this sort of main term, just like we saw before, P to the N, but now minus a bunch of terms, namely 2G. So that's like the size of the 2G is how many, is the size, is the rank of the first homology of this G whole torus. And all those alphas, all those numbers have absolute value of the square root of P, and then you get this +1. So this is just like sticking in more of these oscillations. I haven't actually done any examples of that myself. It would be fun to see how those work. So I mean, of course, there's still a lot of mystery involved. Well, not only why it's true, but also just even like what are these alphas? So I mean, like how do you figure out what these alphas are? If someone hands you a curve. I actually don't know that much about that. I should. Well, I know it. I guess I know what they are in some super abstract sense, but I don't know how to. I wouldn't like be able to be very good at guessing them, getting them. So of course, there's the simplest example, which is the curve of genus 0, which is the projective line. And so then you don't get all these annoying square root of P type corrections. So you just get like P to the N +1 or Q +1. And there, it's really clear what's going on. You and I spent tons of time talking about this kind of stuff. Jim, probably I learned it from you or something, that we're just, you can split the projective line into a copy of that affine line that has Q points and then a point at infinity. So in that case, those are the motives. Those two things are, I mean, they quote are the motives. They're the pieces of your variety that explain these different terms. And a completely obvious way that wouldn't make you think about motives because they're just like geometrical pieces. Of course, there's arbitrariness in how you decide to chop the projective line into an affine line and a point at infinity. There's no particular point that's the point at infinity. And that sort of flexibility of how you chop it up, I guess, is also sort of shows up when you think about more fancy motives. But in this case, it's the decomposition of this count of points into terms is very, very intuitive and geometrical.
Am I supposed to?
Yeah.
Am I supposed to understand the picture for that projective line? I thought I understood the picture.
This one?
Pictures, yeah, the pictures for higher genus. I thought I understood those pictures a little bit better than I understand this picture. Maybe because this picture is degenerate.
Yeah, this is a 0-hole torus.
I'll have to think about it, but
yeah, it's a degenerate case, and so you're not getting these one cycles, these non-trivial first homology, which is like the tricky.
I mean, maybe you tricked me, but with the higher genus pictures, I thought I could see the pieces that you were drawing and how they corresponded to the terms or something like that.
Well, you sort of can. You sort of can, except of course you have to.
Maybe you just didn't try to draw this picture as accurately as you did through the other ones. I don't know.
Yeah, well, I'm too cheap to draw pictures. So yeah, I mean, I didn't draw these one cycles that are like you've seen probably like like you have two. Yeah, so you could do that. I mean, but the main thing, of course, that's mysterious is that like the way that those things contribute to the number of points in your curve is not by adding some extra numbers, it's by subtracting some extra numbers. So I mean, you can, so these, and well, even worse, they can be they're powers of a complex number. But so they could like, but depending on what's going on, they could like either add or subtract to the total number of points. So thinking of them as things is very mysterious compared to the even dimensional cases, because they're like negative things that can subtract off points or oscillate, or imaginary things. So that's where the mystery of motives starts becoming mysterious, is that they have this complex quality that's you think sort of think of more of as like wave forms or something than just like counting points in something. And then it goes on, and so you know that like if you can start looking at higher dimensional ones, higher dimensional varieties, but some of them are easy. So like the projective plane has q squared plus q plus 1 points. And there again, it's really easy to see that it's because you can break up the projective plane into these chunks that have that many points. And the same for higher dimensional projective spaces. And you know all this stuff, so I don't need to tell you this stuff, but like for any dimension, you can do this way of chopping projective space up into Schubert, I should say Schubert varieties, probably. It's probably what they really call them. They're copies of affine space of different dimensions. And so you can just add up the number of points in them, and you get the polynomial in Q, that's how many points are in the whole projective space. And then it goes on. You could do flag varieties of other kinds, and the same game works. So, but the point is that those are still like really special cases as varieties go. I've just discovered, by the way, that there's something called pavings of varieties. I started asking around, like, what's the most general case in which you can like chop up a variety into cells that are, or sorry, to like open affines that are like these Schubert varieties. And it turns out that there's like a theory of them called pavings of varieties. So there should be like something you can do that's like goes beyond flag varieties, where you still can count points sort of just by chopping up your thing into chunks. And I want to understand that because that's like the easy stuff in some sense. But we want to do the hard stuff. So elliptic curves, you see that they're weird and they have like odd dimensional pieces, and over the complex numbers, that is, they have thought of as a real manifold. So that's already weird. They have odd dimensional parts, and over finite fields, then their number of points has these terms that grow like the square root of p and are negative and are complex. So that's where the Weil hypotheses really get their interest. So here's the Riemann hypothesis part of the Weil conjecture. So very often people talk about the Riemann hypothesis part in terms of the zeta function of a variety. But I decided it's better, at least for this talk, and maybe better in general when you're trying to explain it, to just express it as a formula for the number of points, like we were just doing. So here we've got any old d-dimensional smooth projective variety. Say it's defined over the field with p elements. So look at its number of points over the field with p to the n elements. And here's the formula for it. So it's a sum. So first of all, it's a sum over the numbers from 0 to 2D, which are the dimensions of the dimensions. So if you change your mind and think of this as like a complex variety, as a real manifold, it would have dimension 2D. So it would have homology going up to or cohomology going up to 2D. And so we just sum over all those dimensions. So it's just like summing over the dimensions of stuff. And then, so if you're in dimension K, you're going to get a bunch of oscillatory, potentially oscillatory terms. And you're going to get one term for each of the, well, you look at the kth Betty number. So you look at like the rank of the kth homology group or cohomology group, and you get one term for each of those, just like we were seeing in the elliptic curve, or in the curve case, but with other homology groups. And then you get this minus sign coming in that's either a plus or a minus, depending on whether you're doing even or odd dimensional homology, just like we saw, kind of alternating sum kind of thing. Should remind you of Euler characteristics and stuff like that, I guess. And then times the nth power of some numbers. And these numbers are complex numbers whose absolute value is your prime p to the k over 2. So that's just, all this is sort of the straightforward forward hoped the, the easy extrapolation of what we saw in the curve case to higher dimensions, I guess, with maybe the minus alternating minus signs, maybe being subtle, but I guess you could have already guessed it. So usually this is phrased in terms of a zeta function, and it's about the locations of the zeros and poles of that zeta function. But I don't really want to talk about that now, because I don't think it actually helps for what we're doing now. So it helps. What this is suggesting is that, like, there's some mystical way that you can take your variety and chop it up into pieces, where you get like a bunch of pieces of each dimension, and then within each dimension you get like a number of pieces that's the Betti number of that dimension. But these pieces we've seen have got to be sort of mystical pieces, because their contribution to the number of points could be complex. And so these pieces are going to be motives. These are what motives are supposed to be. I think I told you all of this stuff. So the rate at which the number of points grows depends on just the dimension of the motive. And like p to the k over 2 times n, and then they oscillate. Yeah, so that's that. So that's all there is to it. So that is where I've gotten in writing my talk. And so that's just like supposed to show you that, like, you could get interested in this business of chopping things into motives, even if you had no idea of what the motives were going to be. And I've sort of secretly been using the idea of étale cohomology, which is the idea that you could take a variety over a finite field and somehow or other some corresponding variety over the complex numbers. The topology of that is supposed to, like, tell you some information about the finite field case.
Say that again. What?
If you have a variety over a finite field,
Yes,
you have some kind of cohomology groups that are like the cohomology groups
like the code.
of the corresponding quote unquote complex variety.
Yeah.
I guess if your equations are defined over integer with only integer coefficients, then this exact same equation can give you a variety over any field. So then corresponding sort of makes sense, but I can't. I think the way it works is that, and this is like where my ignorance comes in. I think the way it works is like you could take a variety over a finite field, figure out a way to write it down as using just the integers, just like write it as a bunch of polynomial equations using just integers. So you're like picking a scheme over the integers, and then you can specialize that down to the complex numbers again. But there's like some choice in how you do that. But the cohomology should work out the same no matter how you do it, which is sort of amazing. So that's that. And so the other thing that I've been doing is like trying to understand what are motives actually. And you may know that stuff just about as well. But I've like finally gotten serious about trying to learn about it. And they're like different, it's made a little bit harder by the fact that there are like lots of different kinds of motives that people talk about, like pure motives and mixed motives and Chow motives, which is an orthogonal distinction. And like how any adequate equivalence relation gives you you can use it to give you a notion of motive. And yeah, remember you were like showing me, I don't know, you got me to look at Wikipedia about that, and you were saying like, oh, why did they say this one is the coarsest one and stuff like that? So numerical equivalence is nice. It's the coarsest one. And it's one reason why it's nice is because so to get motives, you sort of take the pure motives, you take the category of smooth projective varieties and you massage it to make it vect enriched and then make it Cauchy complete. You Cauchy complete it. I mean, this is, well, there's more to it. That's a sort of sloppy way to say what you're doing to it. But when it's done, it is those things. And then you invert the Lefschetz motive, which is like the affine line, seen as a motive. And then I guess what's so great about numerical equivalence over all the others is that it's the only one that gives you a semi-simple category when you're done, which I don't really understand that yet, but at least I like that. So then you can very beautifully chop something up into motives, chop any variety up into motives, because semi-simple categories are really nice.
Yes. Well,
things up. So I want to understand that stuff better.
Yeah.
And I guess what I really want to do, and I'm just beginning to do it, is like try to really understand the motives of curves, the motives that show up when you take curves and do them and chop them up. So those are called one-dimensional motives, and it turns out that like people have thought about them, and they've thought about something that they call one motives, which are not the same, which are one motives are like all the motives you get from starting with the one-dimensional motives and doing things like tensoring them and adding them and so on.
All right, wait a minute. I'm getting slightly confused about this. So
this isn't a talk anymore.
Sure.
Blathering.
Well, I mean, for one thing, I am tempted to go back through the slides and ask all my questions.
That's fine. That would be great.
By using the slides to cue my questions. But before I do that, I'm just trying to get some sense of this terminology you're talking about. So
yeah, I was talking about one-dimensional motives.
Yeah, I mean, so okay. I mean, I was getting the sense that, okay, so the one-dimensional motives was, are we still? Yeah, okay. The one-dimensional motives, those are the ones that correspond to one-dimensional pieces.
Right.
And then you're talking about something more general called one motives, perhaps.
Yep.
And those are built in some way out of one-dimensional motives or something like that?
Yeah, I think it's something like the two-rig, the sub-two-rig of, well, it's I still don't quite understand it yet, but it's something like the sub-two-rig of motives that's generated by one motives. It might just be generated by direct sums and tensor products rather than any co-limits.
Yeah, it might be something
like
that.
But I'm not even sure. So Dolan wrote a paper about one motives where he gave like a geometrical description of one motives. And so I don't understand it yet because it's a little funny, but it's sort of like what you might think, that it sort of seems to be like it would include, I mean, it should include like products of elliptic curves, clearly. Well, no, why did I say obviously? Oh yeah, well, yeah, I don't know if you throw in the Lefschetz motive should be like a 2 motive. It's like, so So
The
he
Lefschetz motive should be a 2 motive?
yeah, when I say one-dimensional, I mean, well, I don't even know. There are two things you might mean by one-dimensional here, right? You might mean like you might say an elliptic curve is one-dimensional. Or you might say, well, no, an elliptic curve has cohomology going up to degree 2.
Yeah.
And then there's like the two-dimensional chunk of an elliptic curve, which is just the Lefschetz motive. It's just like it's just like the affine line. Sorry.
Say that again. What
I mean, the reason why it's so confusing is, right, there are two different dimensional numbering schemes here. One is the one that you see with your lying eyes. That's like some joke phrase.
Yeah.
Like your lying eyes tell you that this donut here that I'm trying to find is two-dimensional. That's one numbering scheme.
Yeah.
And then there's the one which your educated sensibility says this is a one-dimensional variety.
Yeah, it just basically just sounds like real versus complex viewpoint. Yeah.
Yeah, right. But I mean, but that numbering scheme shows up over in the finite field case too. That difference in numbering schemes.
Okay.
So anyway, so I don't even know if a one. So the motive of this elliptic curve consists of this bulk, this big fat thing, right? And then these two circles and this dot. So the big fat thing is the Lefschetz motive.
When you say the Lefschetz motive, what do you mean? Does each thing have its own Lefschetz motive, or is it just this?
No, there's one motive.
The whole category of motives. There's one thing called the Lefschetz motive.
Yeah. So the Lefschetz motive is, if you wanted to visualize it as a thing, it would be like the affine line. So it's like the projective space, projective line minus a point is the Lefschetz motive. So it's the Lefschetz motive is the thing that has p to the n. If you want to talk about how many points a motive has, which is probably sort of funny way of talking, but it is sort of the whole point of the motives. The Lefschetz motive is the thing that gives you p to the n points when your field has p to the n elements. So it to the extent that it is some kind of variety, it's the affine line. So there's not lots of Lefschetz motives. It's just that thing.
Okay, but I'm still having trouble deciding, I understand in what sense the affine line is supposed to be incorporated into an arbitrary curve, an arbitrary, let's say, non-singular curve. But okay, I don't have to worry about that right now. So, and then you talked about inverting the Lefschetz motive.
Yes. So that's one. I don't know deeply why people do that as part of defining.
Well, can I ask about that?
Sure.
I'm not going in order here. I had some idea about trying to ask you questions in some systematic order, but I've instead just jumping around asking random questions here. So this bit about inverting the Lefschetz motive, it reminds me of something. So it actually reminds me of something about the belief method and about the possibility of developing a homotopy version of the belief method. But what am I trying to say? That so the homotopy category of spaces is, well, for one thing, it's sort of like, I mean, this is a trite thing to say, it's like a homotopy version of the category of sets, in the sense that, the category of sets is sort of the foundation on which everything else is built from certain viewpoints. But, in in the how do I say this? Well, let me think that. Let me think about that for a second. So let's see. Okay, let's think about that for a second. Let's think about the category of sets, and let's think about it as, you know, the theory of nothing in the doctrine of what do we call them? We call them. We don't call them absolute two rigs. That's usually when we're doing Todd's version of stuff, but we call them
complete.
I thought we had a different jargon for it. Absolute two rigs.
Total?
Total, yes, that's what it was. Right. Yes. Total two rigs. Again, completely stolen from or borrowed from Todd or something like that. So here's a little bit of the belief method that we didn't talk about. I don't recall us talking about yet. Supposing you start with the theory of nothing, with the syntactic category is the category of sets. And again, we're working with applying the belief method to the doctrine of these total two rigs. And so in this theory of nothing, the initial object is, I guess, what's sometimes called strictly initial. It has no points, no global points. But you could try believing in one. Saying that right? You could try believing in that. And anytime you try to believe in something, there's always some danger that what you're trying to believe in is so inconsistent that it will cause your whole syntactic category to collapse down to the inconsistent theory or something like this. But this one you can actually believe in this doctrine without too much of a disaster happening. And so what happens?
Category of pointed sets?
Yeah, that's right. That's right. It ends up being, yes. So the point turns out to be equivalent to a belief in this map from the tensor unit to the initial object.
Huh, that's nice.
So it's the category of pointed sets. And it kind of stops there. If you try to believe in another one, it just automatically coalesces with the previous base point. You know, so if you believe in it twice, it's still just like believing in it only once.
That's true of a lot of things.
All right, I'll think about that. But so everything I just said is rigorous, but let's play with a non-rigorous version. Let's imagine developing a homotopy version of the belief method. So that would be, you know, the whole belief method is based on colimits. So presumably the homotopy version of the belief method would be based on homotopy colimits. And presumably based on Brown's representability theorem, which on good days, maybe I understand what that actually says, but I'm not going to worry about what it says right now. But that's how you would get the mechanics of the homotopy belief method to work, if it works at all. So I'm just, you know, throwing out the idea that if you did this in the homotopy world, you'd probably get the category of pointed spaces instead of the category of pointed sets.
The first time.
Yes, the first time. Well, but also the second.
Oh darn! I was hoping that you'd like there'd be like some wrinkle, but okay.
There'd be a wrinkle, but it would just be homotopy equivalent to the first one. You know, you'd have the point would look like a wrinkle or something, but the wrinkle would be just an interval with two endpoints. So it would be a contractible wrinkle. It was really just like a base point or something like that. I think. I'm throwing this all out as though I actually know how it works, but that's what I think would happen. But so I just brought this up as a springboard for some next step that we want to take. So as soon as well, so as soon as we introduced the base point, well, remember, I mean, part of the whole doctrine is that we had a tensor product, and in the theory of nothing, that tensor product was really just Cartesian product. But in the doctrine, it doesn't have to remain Cartesian, and clearly it's not Cartesian when you start believing in this global point of the initial object. Because then you got base points, and the tensor product is, I'm hoping I got the right name. I guess it's called smash. Is that right? Smash. Yeah. Again, smash is probably overblown terminology if you're talking about pointed sets, but it's not overblown terminology if you're talking about pointed spaces. That probably is what smash is. So the tensor product here is smash. And again, we're doing these two cases sort of on parallel tracks, the non-homotopy case and the homotopy case, sort of pretending that we can handle the homotopy case as easily as the other case. And so here's something, now that we've, go ahead.
Very stupid question that I could figure out the answer to, but I'll just ask you anyway, which is, so smash product is non-Cartesian. Is that like one of these semi-Cartesian guys?
That's like a good question. Right, it sure sounds like it's semi-Cartesian, but I couldn't tell you which half. Is it obvious? So let's see.
I think the unit is still terminal.
It really is?
Is it?
Unit? No, I think the unit is what I would call the zero sphere.
Oh, okay. The zero sphere?
Yeah, because it has its base point, but it also has its identity point or something like that. So it's got 0 and 1 kind of.
Oh, right. Yeah, you need that. Yeah, otherwise, right, it wouldn't be the smashing with just the 1.7 to kill everything. Yeah, right. Okay.
Yeah, I wouldn't be surprised if it's maybe semi-Cartesian in some complementary sense, but I don't want to worry about that right now.
This is not what I normally mean by semi-Cartesian. This is
okay.
Okay.
So it seems like it's such a short distance away from the original Cartesian state that seems like maybe there is still some vestige of Cartesianness there, but I don't know. I don't want to worry about that right now. So let's see. So we have, am I saying this right? So the smash unit is what we just said, the zero sphere. Is that right? I think that's right.
That sounds right.
Okay. But now let's think for a moment that we're working in the homotopy case again. It's sort of fun to think about this kind of thing in the non-homotopy case, but I'm going to think about it in the homotopy case. So the zero sphere, which is basically, discrete 2-point set. That is the smash unit. But now let's think about the one sphere in this infinity comma 1 category or whatever it is. In this homotopy world, this homotopy category of pointed spaces or something like that. So so what if we tried believing in a smash inverse for the one sphere? Do you have a sense of morally what that should produce?
I think you should get spectra.
That's right. That's right. That's right. I mean, we have to make that into an actual theorem, but I think you've got the sense of why it's a pre-theorem. why it wants to be true. This is the way we should think of. And in fact, if you look at, the classical, some of the really original classical definitions of what a spectrum is, in terms of a certain, I don't know, it's an inverse limit or direct limit or something, a formal inverse limit. If you look at that really is very much like a believer. It's exactly the kind of thing that you would, if you took the belief method and then sort of homotopified it a little bit, and you tried to believe in a smash inverse for the one sphere, then we should be able to turn that into a theorem that under the homotopy belief method, that produces the space enriched category of spectrums.
Huh.
And so it's kind of a very long-winded question, but you kind of see where I'm going with this. I mean, that really feels to me like what you're talking about inverting the Lefschetz mode. It really sounds like it's some sort of analog of that. Am I totally on the wrong track? I mean, it really feels like that. But in what sense is this Lefschetz mode that you're pointing to in the picture here, pointing to in this picture here on my screen, in what sense is that some moral equivalent of the one sphere, or something like that? I mean,
yeah.
Is it like
Yeah, I mean, it's almost, so it's the Q here, and this Q plus one it gives you the Q and the Q plus one. So it's not, I don't see how it's like the one sphere. It seems like it plus one is like the two sphere, or the projected line, if you want to think more complexly. So it is sort of funny that people want to invert the Lefschetz motive instead of, like, you might think of like you might have thought of like trying to invert P1 as being sort of
P1,
more obvious thing to think of inverting. I mean, P1 is sort of it's
invert the
sort of like
Lefschetz
the
motive.
it's the two sphere.
All right, I'll have to really think about that. But there's something that's going on here, and I'd like to understand it better. And I'd like to understand, like I say, I honestly believe that you can retrace the historical development, the historical invention of the stable homotopy category. And you can see that as a great example of the belief method, except that, as usual, as so often happens, the original example is actually more complicated than the earliest formalized case. So it's a homotopy belief rather than a mere belief. And I don't know, to what extent does the formalization of homotopy belief, to what extent does that end up being a sort of circularly motivated program? I don't know. But so this is interesting. The affine line. Well, the affine line, let me try to, in some very silly way, let me try to make the affine line sound like an analog of, no, that's not going to work. I can say an analog of the one sphere. I think it's more like I can make it an analog of the zero sphere. Let's see. Because I mean, the affine line is sort of a formal difference between the projective line and the projective point or something like that.
Yeah.
So I don't know. I'll really have to think about that.
One thing that, here's something that could be some clue, but I don't know how.
Yeah.
Is people say that so far that when I try to read, like, why do you invert the Lefschetz motive? One thing people say is that if you do that, it makes your category of motives become, well, they say rigid. All objects get to have duals now.
Again, that sounds a bit like with the stable homotopy category.
It sort of does, sort of.
Yeah, there's some family resemblance there. Go ahead, yeah.
Yeah. So I saw in Math Overflow some hapless person asking and not getting an answer to, like, why invert that thing? Why does inverting that make everything rigid? And if you wanted to make everything be rigid, why didn't you just make everything be rigid? Why didn't you just say, like, we'll give everything a dual? And nobody answered those questions. So I'm still, and I'm not smart enough yet to figure it out myself. So I don't know what's going on there, but it's got to be part of the story at some point.
Well, I mean, it sort of seems like if everything has a dual, then the Lefschetz motive will have a dual. And then maybe that's so simple that that dual will have to be an inverse. And then somehow you prove that that one inverse is enough to get all the other duals somehow. I mean, that's not very explicit, but maybe that's the rough.
Yeah, it could. Yeah, it could be. I guess. Yeah. Okay. So, like, one practical quiz question to myself is, like, okay, so, like, what's the dual of P1 then? So you're not, like I was just saying, like, hey, what, you could try to invert P1. Well, I guess we're not going to invert P1, but at least we're going to give it a dual. So, like, what is that? I have no idea what that is. So, which means I just don't know what's going on, but it should be something nice.
So the naive analogies that I'm suggesting here between formally smash inverting the one sphere. Yeah. Okay. So you talk about formally inverting. I'm not sure you used the word formally, but you probably meant it. Formally inverting the Lefschetz motive. I don't recall you specifically saying smash inverse or something.
It was in this. It was for this tensor product of motives, which for varieties was like the Cartesian product of varieties. So it's not so much a pointed thing, I don't think.
Well, but okay, but let's remember this. Consider let's do some very simple case. Consider the category of sets, but now consider the category, I hope I'm going to do this right. Consider the category of sets and partial maps.
Mm-hmm.
Partially defined maps. I hope that's fairly unambiguous. Have you thought about this? Have you read about this?
I know it's the category of pointed sets.
Yeah, that's all I meant. Yeah, that's all I meant. So maybe that's what's going on here. Maybe, right? So the equivalence that you're talking about there is with the idea that once you're dealing with partial maps, that's sort of morally equivalent to implicitly giving every object a point at infinity, a base point at infinity. And maybe that's what's going on here. Maybe we're secretly interested in some sort of partial maps between these objects or something like that. I don't know. I mean, right? Certainly, right? I mean, it's at least true. Right? Getting something to be invertible with respect to Cartesian product, that doesn't happen a lot.
Right.
Whereas getting it to be invertible with some other tensor product is much more plausible. And
also,
so I'm guessing that there is secretly some smash aspect to this newly formally adjusted product, tensor product, whatever. You were going to say something else? I interrupted you.
Yeah, I was going to say that a part of the construction of the category of motives that I completely skimmed over, which is really important, is you start out with not varieties and maps between them, but varieties and correspondences between them.
Right, and that could be related in some funny way. I don't know how.
It's a little bit like partial maps, just a little bit.
It includes partial maps. It includes partial maps,
yeah,
but
right.
it also feels more general than that. It feels more general than that. But I'll have to think about that. But I was also going to comment that, some of the very naive analogies that I'm suggesting here, between formally smash inverting the one sphere to get the stable homotopy category, or the stable homotopy infinity comma one category, or something like that.
Mm-hmm.
But that's in some way analogous to something where you formally invert, with respect to some kind of tensor product, formally invert the Lefschetz motive to get motives. So in other words, I'm just suggesting a very simple-minded analogy here. And it seems to be going something like spaces are to spectrums as varieties or schemes or something are to motives. Just the vague idea that maybe motives are just like a stable, well, let's see, but.
Can I give you some evidence in favor of that before you give evidence against it?
Sure, but I did come up with some evidence against it, but go ahead, yeah. I mean, it's more complicated than what I said, but go ahead, something like that.
Yeah, one thing that's very appealing about that slogan is that spectra were invented to turn generalized cohomology theories into representable functors, and motives were devised to be sort of the universal cohomology theory for varieties. Those two sentences aren't completely parallel yet.
Right, but there's something like that.
But I think they are basically parallel. So the idea is that like here's a way to make them sound more parallel, is that like any cohomology theory for spaces should factor through spectra, and any cohomology theory, definitely any cohomology theory of the kind that Grothendieck was interested in, I guess they call them vague cohomology theories, are supposed to factor through motives. And it's supposed to be sort of like the universal thing that makes that true. That was sort of like the idea. So those sound pretty, that makes it all sound nice.
I'll have to think about that. The thing I was beginning to think I had wrong was, we have this idea that inverting the Lefschetz motive is really just the finishing touch on a process of building the category or whatever it is of motives. But we also did some preliminary work before we got to the. Yeah. I mean, we just made it pointed or something like that. But maybe there's something like that going on. That could be. I'll have to think about that.
I'll also add one extra piece of evidence. It's like, again, over my A grade.
Yeah, sure.
So in addition to these motives that we're talking about, Grothendieck and people were trying to dream up mixed motives, which were supposed to be for not just smooth projective varieties, but for arbitrary projective varieties.
But I mean, it sounds like as soon as you're talking about the Lefschetz motive, you're already implicitly talking about, I mean, aren't you saying that the Lefschetz motive is the prototypical mixed motive, or did I misunderstand?
No, it's a pure motive. You're starting out with projective varieties, and then when you're doing this Cauchy completion, the Lefschetz motive appears, because the way it appears is good to say, by the way, that so there's a map from like the projective line down to a point, and then you can include the point back into the projective line.
Yeah.
So there's a map
Yeah.
from the projective line to itself that squashes it down to a point, and that's idempotent.
Yeah. Yeah.
And so then when you do this Cauchy completion, you split that idempotent. And so what you're doing then is you're splitting the projective line into a point and the other stuff. And the other stuff is the definition of the Lefschetz motive. It's the I don't know why I said that just now. Oh, well, because to show that it's
Yeah, no, that's it's very relevant, but it's also confusing me. It's you know.
Well, the reason why I mentioned it is that, like, we didn't bring in any non-smooth
Yeah.
varieties to get this thing to show up. But anyway, the thing I wanted to say was that.
So singular things, okay.
Yeah.
I thought but the reason I said what I said, which maybe didn't make much sense, but it's just I thought I remembered that, you know, people talking about things like, you know, first they tried to define these things just for, like, you know, complete varieties, such as projective varieties or something like that. And then they started generalizing beyond that. And one of the initial stages of generalization was to the case of affine things as well as complete things. But maybe another stage is, you know, having singular things rather than non-singular things or something like that.
Yeah.
Yeah.
I think you're right. But anyway, what I wanted to say though was that so nobody could ever get a category of mixed motives that did all the stuff that people wanted, like, had all the nice features that people wanted, apparently.
Yes.
And then what Vygotsky did, which everyone got so excited about, is he sort of succeeded, but the way he succeeded was really, they claimed, to make an infinity one, basically. I mean, maybe he didn't say it this way. He made an infinity one category of mixed motives, and
right,
sort of skipped over the getting the category of them.
right.
So the only reason why I'm mentioning all that fancy stuff is that it sort of plays into your story that's trying to, like, analogize motives to spectra and, like, the homotopy belief method. So,
Yes.
maybe if we understood this better someday, we would like to see how mixed motives show up from this kind of story.
So by the way, I'm not really following the clock very much. It could very well be the case that we might or should get thrown off. I should get thrown off my computer I'm using here at some point, but that's okay. We'll just, you know, we might continue from my house or something like that, or we might just quit until next week or something like that. But what was I going to say? I had another idea to throw in here. Again, I'm not going in a very systematic order. I'm just giving you some off the top of my head reactions to things you're saying here. So part of the time when you were talking, you also made it sound like the whole motive project is a relative of some other project that you and I played around with a pretty long time ago, probably unaware that it was connected to anything anybody else was doing. And that was when you and I played around with sort of trying to categorify zeta functions and L functions and stuff like that. You know, so these zeta functions or L functions, whatever they have, terms or factors or something like that. And they're just, you know, those are very decategorified things if they're, you know, if they're just zeta functions or L functions or something like that. But if you start trying to categorify them, perhaps particularly the factors, like the Euler factors or something like that.
Yeah.
I mean, there's also all sorts of games where you take the logarithm of a zeta function or an L function or something like that, and the Euler factors become sort of Euler terms or something. I'm not sure what they're actually called. Just because of the nature of logarithms. Yeah.
Yep. Yeah, I mean, that logarithm thing, by the way, just is like really running around here. I was trying to sort of
Sure.
avoid it, but like the way that like here we're getting these terms that grow like p to some power.
Sure. I mean, there's, the issue of, do you talk about zeros of a zeta function that live on a circle, or do you talk about them living on a line or something like that? And it's just, am I saying this right? The line exponentially wraps around the circle, and that's part of the deal.
Right. Yeah. So that. Right. So in this talk, I just like tried to not, after like a little brief intro to zeta functions, to the Riemann zeta function, I sort of switched over, basically, I guess, sort of by taking I don't even know if I'm exponentiating or taking a logarithm.
Right. Yeah, it gets very confusing, actually. Yeah.
Switched over to a more count of points type of thing. So I guess, yeah, so like if you take a disjoint union of two things, the number of points adds, but the thing that's like the zeta function, I guess, multiplies, if I'm correct. It's very confusing, actually.
Yes, but you're making it sound to me at a very naive level, like, our old crude attempts to categorify zeta functions and Euler factors thereof, and Euler factors of L functions, whatever. That semi-consciously, those crude attempts were like a crude attempt to invent or reinvent motives or something like that.
Yeah, I guess so. Yep.
Also, I got a little bit confused. Okay, so you're staring at the same picture on the screen. You see the picture that I'm staring at the screen. So you've got like an elliptic curve. You got an elliptic curve. It's got a little orange meridian, a little purplish pink longitude, and they intersect in a little blue point. And I just got a little bit confused, and I don't even know if you wanted to come down on one side or the other. But those two little one-dimensional pieces, the origin meridian and the purplish longitude, are those supposed to be two separate one-dimensional motives, or are they supposed to be lumped together into the one-dimensional motive, or
oh boy,
were you being that precise? You were being.
I was not trying to be that precise.
Yeah.
Right.
Because sometimes you said, like you take all the pieces of dimension k, and that sounds like the k-dimensional motive or something like that. But other times I couldn't tell.
Right.
What you were saying.
Yeah. So it's like, yeah. So I don't know. Is the terrible answer. So what
no, that's fine. That's fine. Go ahead.
So what I really should do, I mean, at least, so the way you would answer that, is that you would look at how you'd like work in characteristic P, and you'd look at how the Frobenius acts on the first cohomology, the first étale cohomology, and you would see if it's acting in a way that like it would have, I think it would have two separate eigenspaces. It's a two-dimensional cohomology group, and I think if it acts in a way that like preserves two subspaces, then each of those subspaces corresponds to a motive, like an irreducible motive or whatever. But I don't. So that makes it sound like if that's true, then you could like chop the one-dimensional motive into two parts. The one-dimensional part of the elliptic curve into two chunks. But I find it dubious that those two parts correspond to these two parts here.
Yeah.
Because there's no way in the world that like one of them could have to do with alpha to the end and the other could have to do with alpha bar to the end, as far as I can see anyway.
Yeah. Okay.
Not able to know which one is which. So in some weird way, maybe these are like connected to like the sum and the difference of these two picked pieces or something like that.
Or
but
something, or something.
Yeah.
Or
So,
okay, I'll have to. I mean, I was sort of expecting you to fall back on just saying that you're not really trying to give, not necessarily trying to give separate identity to each different term, but rather just to all the terms of a given degree or something like that. I don't know. I don't know.
yeah,
But
well, I mean, I can certainly fall back on that if I want to like
yeah,
not admit how little I know about what's going on. But
right.
but there is this way to, well, when you're at least when you're working with well, you can always decompose motives into indecomposable parts. I mean, if you're smart enough.
Okay.
And so there's like a question there, like is the one-dimensional motive of the elliptic curve, is it a single irreducible thing, or is it the sum of two irreducible things? So I should know that. I mean, I should, because I'm talking about this. So anyway, that's a question that's like a good question.
Yeah, I just don't even have any good feeling for the answer to that. But what was I going to say? So I'm beginning to get the feeling that I also, perhaps very similar to you, I am also very interested in what happens in this numerical equivalence case. You know, if you can really actually see very concretely what this alleged category of pure motives is, and how it is something like semi-simple or something in that case. That would be nice to see that very concrete. I mean, just to be able to see that, I'm hoping that would, right? There's so many things that we're saying that I only halfway understand. But if we could work out that one example in more detail, I have a feeling that it would become a lot more clear what are the things that we really actually can understand versus the things that really are still tricky to understand.
I mean, I think that the whole category of all the motives there, I think it's sort of big and, I don't know, I think it's sort of scary.
Yeah.
But like for the ones that you get from like elliptic curves or maybe from other abelian varieties, that seems like maybe something that we could like.
Yeah. Just give me like 15 seconds. I'm just trying to make sure that like I'm not doing something wrong here, that I'm not like display. Yeah, I just have to find out. Just give me 15 seconds or so.
Sure.
All right, it sounds like it's actually a reasonable thing. It sounds like my friend says we should try to quit at 7, which would be about 10 minutes, as he says.
Okay.
And that might be enough for tonight if we just finish in 10 minutes or something like that.
That'd probably be good for me. Yeah.
Okay. So let's try to aim for that. So. I mean, you can say anything you want here, but I mean, what I also want to do here is, again, go through these slides and just ask any questions that I thought I remembered coming to my mind when I was. I would like to start somewhere near the beginning.
Yeah, I'll do it.
Okay. Because I probably have really dumb questions about every slide.
Okay, well, is that one?
Well, I think I already asked my dumb questions about this one,
okay,
or made my dumb comments. Okay, next slide. All right, let me, I'm sure I have dumb questions about this one. So let's see. Right, my dumb question, I mean, you probably already answered this dumb question, but it was something like, I mean, This vaguely reminds me of things I never really understood when I was reading Ramanujan biographies. That so you're talking about Riemann actually came up with a sort of analytic expression, so to speak, a formula in some sense for a step function. Is that right?
Yep.
And that's what this is supposed to be depicting, a step function with that degree of step likeness. But presumably the sense in which that is a formula is not a very precise sense. I mean, it's not like you can very easily define what is a formula and what isn't a formula or something like that. I don't know.
I'd get the thing that there's really a nice formula for is this von Mangold function, which is about not counting not just primes, but also prime powers and counting them weighted in some way, which I can't remember, or like you count the nth powers as giving you a certain jump that depends on n.
You know, again, when I read pop biographies of Ramanujan, they make it sound like, you know, he was so out of touch with the mathematical community that, you know, he would, and this is really probably because the pop biographies are illiterate, but
Yes, sir.
but that he would make somewhat outlandish claims about having a formula in some sense for the exact number of primes or something like that, which was presumably supposed to be better than whatever it was that Riemann had. And that, I guess part of the story they tell is that, you know, this was one of those things that allegedly Hardy had to educate Ramanujan about or something like that.
Yeah, I've heard that.
But it could be such a distorted story. I have so little understanding of what was really going on. Anyway, that's why
I've heard it, and now you're making me want to dig
up on
into
the history. Yeah.
Yeah, I got a hold of all these books in electronic form, which are books where like people have gone through all of Ramanujan's notebooks and like figured out how to prove all the stuff that they could prove. And
yeah,
I don't know if, I think it was in one of his letters to Hardy that he was making boastful claims about all the stuff he could do. So yeah, I really want to know now what that is.
Yeah. So anyway, that was my silly comment about this slide. Let's go to the next slide.
Okay, so the next slide, you actually see the formula in action.
Yeah, boy, what does this remind me of? I mean, it reminds me of all sorts of pictures of. I guess what it's doing, it's giving me visual mental flickers of the Gibbs phenomenon or something.
Right, you can see the Gibbs phenomenon here happening.
And then there was that funny Gibbs-ish, meta-Gibbs-ish phenomenon at the prime powers. Okay. Yeah. Oh, well, okay. Here's some more stupid questions. So, making it sound, well, okay. So I mean, one of my comments here is that, you know, you're sort of motivating the motive story in terms of the Riemann hypothesis story. I mean, that's not a perfect description of what you're doing, but it's a little bit of what you're doing.
Yep.
And one of my reactions to that is that, you know, this sounds like one of those cases that I claim always happens to me where, you know, the thing allegedly being motivated is the thing that seems completely obvious to me, and the thing they're motivating, it turns out, is something that's totally alien to me. So, but nevertheless, there's something fun going on here. And so you've got, right, this famous thing, zeros of the Riemann Zeta function. And you're thinking of them as correction terms in correction terms to add to this very main term. And
By the way,
go
that
ahead.
main
Yeah.
term is
Yeah.
actually coming from all the non-trivial, sorry, all the trivial zeros of the zeta function. That's
Okay, that's
something that I wasn't gonna say in my talk, but it does.
well, but that's great. I mean, I was almost gonna ask that question, but not quite.
Yeah, Monin makes a big deal of that.
Yeah.
And he's like trying to explain how the main term is somehow connected to like the other valuations on the rationals. So like the
Archimedean,
like the mysteries of the real prime.
Yeah. Okay. That's very interesting. I don't know what to make of it. I just want to.
Yeah, I don't know much about it either, but there's supposed to be like a more coherent story.
Okay. So I just want to ask a couple more stupid questions before I quit here. So one of them is you're making it sound like we might order these corrections in some sensible order. I mean, are they like, what's like there's an ordering of the zeros by how
the zeros come in complex
by their imaginary part or something like that. You can just,
the zeros come in complex conjugate pairs.
And is it well ordered? Is it just the order type of the natural numbers? It's the order type of the natural numbers.
I think it may still be unknown whether there are any like repeated zeros of the Riemann zeta function.
Well, okay, but you don't think they bunch up and then skip one and then go to and then start
yeah, no, I mean if I'm allowed to just draw some hasty conclusions from what people have seen about the first few quadrillion of them, there's just like, they're well ordered. They don't bunch up or anything like that.
And that ordering probably is sort of.
That's this
an ordering that
summands in this sum that's being computed here.
Yeah, it's a sensible way to order those summands.
And you see the ones with the higher imaginary part, they make more high frequency type wiggles.
Okay. So yeah, there's something attractive about this. Like I say, the thing being motivated may be more natural to me than the motivating structure. But let's go to the next page, see if there's anything else I want to come to.
Yeah. I mean, it's also true that people understand this stuff much less than the
Right.
Than the Weil hypothesis stuff. But it's also, I think, true that that's why people got interested, at least partially why people got interested in that.
I mean, you're also making me think that, like, there's this. What am I trying to say? You can think of polynomials over a finite field as a sort of mutant version of the integers. They're probably even like a associated graded thing or something of some filtration or something. I don't know. I'm not sure what I'm right about that. But that sounds like part of what's going on here. That if
so the integers are
these mutant versions are more tractable than the original. Yeah. Right. What?
Yeah. So the integers are dreamt of as being a mutant version of it's the mutant version of a curve over a finite field, or the function.
I'll have to think more about that. But let's just go to another page. Another slide here.
That's the main term.
Okay, next. I mean, this is all fun. I halfway understand some of this. Riemann hypothesis. Yeah. Okay, next. Right, and here again, to me, you're sort of hinting that you're trying to categorify the zeros here or something like that.
Yeah, exactly. I am.
So, is there an adjective in front of motives that indicate? I mean, you said what did you say, Manin, or was that a different thing? Did somebody try to talk about the
motives for the
Riemann motives? Yeah,
I think I've heard people say Riemann motives.
Okay.
And Alain Cohn has.
Yeah.
Alain Cohn is trying to work on this stuff a lot these days, and
Okay.
so yeah.
Okay, let's go to the next slide. Let's go to the next slide. I'm just, going through very fast because I'm, well, this is it would be fun staring at these. I mean, I have all sorts of other stories that I want to tell you about staring at things like this. But we'll do that some other day. Let's go ahead. Yeah, boy, I really have a lot of stories to tell you about that. But
counting points on curves, counting points on something.
Yes. Yes. Yes.
No, time's up.
Okay. Okay. We're gonna. You heard that, right?
Yeah, I heard it. Honest to shut up.
Okay.
Okay.
So this was great. I'm really annoyed that I couldn't get the other thing to work, but I'll have to try to have that working for next time. So I'm gonna press the leave button here. But this is very good. Thanks a lot.
Great. Okay.
Okay. See you. Bye.